In order to ensure the basic thermal comfort of the indoor thermal and humid environment in winter and summer, and meet the requirements of building energy-saving design standards, it is necessary to master the basic heat transfer principles and calculation methods so as to control the thermal insulation, heat-proof, and energy-saving indicators of the environment structure, and understand the thermophysical properties of materials. Since the variation law of indoor and outdoor temperature affects the design of thermal insulation and heat-proof of buildings, according to the characteristics of indoor and outdoor thermal effects considered in the design of thermal insulation and heat-proof of buildings, the calculation methods of indoor and outdoor temperatures can be summarized into constant thermal effects and periodic thermal effects. Constant heat action model refers to the indoor and outdoor temperature does not change with time during the calculation period, which is usually used for insulation and energy-saving design of heating rooms in winter. Periodic heat action model can be divided into one-way periodic heat action and two-way periodic heat action according to the indoor and outdoor temperature fluctuation. The former only considers the outdoor temperature fluctuation, and the indoor temperature is regarded as constant, which is used for heat insulation and energy-saving design of air conditioning rooms. The latter takes into account the fluctuation of indoor and outdoor temperature for the summer insulation design of natural ventilation rooms. The heat transfer of the envelope structure under the constant heat effect is a steady heat transfer process. Structures such as walls, floors, flat roofs, domes, and walls with a large radius of curvature are all called flat walls in building thermal engineering. When the dimensions of the width and height of the flat wall are much larger than its thickness, the heat flow through the flat wall can be regarded as only along the thickness direction, that is, one-dimensional heat transfer. Under constant heat, the heat transfer through the flat wall does not change with time, which is called one-dimensional steady heat transfer. One-dimensional steady heat transfer is characterized by 1. The heat flux through the flat wall is equal everywhere. That is, the heat storage phenomena inside the flat wall is not considered, and the heat flowing into and out of any section of the flat wall is regarded as equal. 2. Inside the flat wall of the same material, the temperature distribution of its interface is in a linear relationship. From the flow law, Q equals the thermal conductivity multiplied by the temperature gradient. It can be seen that the thermal conductivity is regarded as a constant, and it can be seen from Figure 1 that the heat flux is unchanged, and the temperature gradient at each point is also unchanged. That is, the temperature changes with distance. The change rule is a straight line. There are more or less poles in general building materials. The heat transfer methods in the poles include heat conduction, convection, and radiation. Since the proportion of heat transfer by convection and radiation is very small, it can be ignored in the thermal calculation of buildings. Only consider heat conduction process. The steady heat conduction equation for monolayer homogeneous flat wall is derived from Fourier's law and one-dimensional steady heat transfer characteristics. According to the one-dimensional steady heat transfer characteristics, the temperature gradient is equal to the ratio of the difference between the temperature of the outer surface and the inner surface of the flat wall to the thickness of the flat wall, and the ratio of the thickness of the flat wall to the thermal conductivity of the material of the flat wall is defined as the thermal resistance. The heat flux of the flat wall is equal to the temperature difference between the inner and outer surface of the flat wall divided by the thermal resistance of the flexible layer. The thermal resistance is used to represent the ability of the flexible to resist heat flow through. Under the same temperature difference, the larger the thermal resistance, the smaller the heat flux passing through the flexible, and the better the insulation performance of the flexible. Increasing the thermal resistance can be achieved by increasing the thickness of the flexible or selecting a material with a small thermal conductivity. The multi-layer flexible is composed of several layers of different materials. Due to the close bonding between the layers, the temperature of the interface between the layers is also represented by the surface temperature symbol set. Note that the number of layers of steady heat transfer should be numbered according to the direction of heat flow. Taking a 3-layer flexible as an example, since a constant thermal action model is usually used for the calculation of the thermal performance of the heating room in winter, the indoor temperature is higher than the outdoor temperature. The heat flow transfer direction is from indoor to outdoor, and the inner surface temperature of the flexible is high. Then the heat flux density of each layer is Q1, Q2, Q3 respectively. According to the steady heat transfer characteristics, Q is equal to Q1, Q2 is equal to Q3, and Q is equal to the temperature difference between the inner and the outer surface, divided by the sum of the thermal resistance of 1, 2, and 3 layers. It can be seen that the heat flux of the N-layer flexible is equal to the temperature difference between the inner and the outer surface, divided by the sum of the thermal resistance of N layers. That is, the total thermal resistance of the multi-layer flexible is equal to the sum of the thermal resistance of each layer. The composite wall composed of 2 or more materials includes various forms of hollow blocks, walls filled with thermal insulation, etc. When the average thermal resistance is calculated parallel to the direction of heat flow along the interface of different materials in the composite material layer, divide it into parts and consider correction for different materials. The steady heat transfer process of the flexible includes 3 processes: internal surface heat absorption, flexible heat conduction, and external surface heat dissipation. The endothermic process of the inner surface includes convective heat exchange and radiation heat exchange. Let alpha I equal to the sum of alpha IC and alpha IR. Then Qi is equal to alpha I multiplied by the temperature difference between the indoor air and the inner surface. According to the calculation formula of multi-layer flexible heat conduction, Q lambda is equal to the temperature difference between the inner and outer surface of the flexible divided by the sum of the thermal resistance of each layer of the flexible. Here is a formula listed with 3-layer flexible as an example. The heat dissipation on the outer surface is similar to the heat absorption on the inner surface, and both include convection and radiation. Alpha E is equal to the sum of alpha EC and alpha ER. QE is equal to alpha E multiplied by the temperature difference between the external surface and the outdoor air. From the one-dimensional steady heat transfer characteristics, it can be seen that Q through the flexible is equal to Qi, equal to Q lambda, and equal to QE. Therefore, it can be concluded that the heat transfer flux through the flexible is equal to the temperature difference between indoor and outdoor divided by the sum of the thermal resistance of each layer of the flexible and the heat transfer resistance of the inner and outer surface, equal to the heat transfer coefficient multiplied by the temperature difference between indoor and outdoor, equal to the temperature difference between indoor and outdoor divided by the heat transfer resistance. In the formula, the sum of the thermal resistance of each layer of the flat wall and the heat transfer resistance of the inner and outer surface is the heat transfer resistance of the flat wall. This characterizes the ability of the enclosure structure, including the air boundary layer, on both sides of the surface to block heat transfer. The reciprocal of R0 is K0. This means that under stable conditions, the air temperature difference on both sides of the envelope is 1 Kelvin, and the heat transferred through an area of 1 square meter within 1 R. The reciprocal of alpha I is Ri. The reciprocal of alpha E is Re. It can be seen that under the same indoor and outdoor temperature difference conditions, the greater R0, the smaller Q. Therefore, R0 is the important index to measure the thermal performance of flat wall under steady heat transfer conditions. Think about it. What is the difference between lambda, alpha, and K? Do air temperature and surface temperature have the same sign?